In a cylindrical coordinate system, a point P in space is represented by an ordered triple R, theta, and Z. The pair R theta in a polar representation, is a polar representation of the projection of P in the XY plane. R is the distance from the origin. Theta is the angle from the positive x-axis. This little square here I did to represent the xy plane. Z is the directed distance from R theta to the point P. So this dashed red line gives you the height above, or if Z is negative, below the XY plane. In order to convert back and forth from cylindrical to rectangular, if you want to go from cylindrical to rectangular, then you use X equals R cosine theta. You will be given R and theta and Z. It's just a matter of correctly plugging those into the conversions. The Y coordinate will be R times sine theta, and Z will remain the same. If you have to switch from rectangular to cylindrical, then you can use these sets of conversions. R squared equals X squared plus Y squared, which R squared is the hypotenuse, X squared plus Y squared. That's that XY plane and Pythagorean theorem together. The angle that opens up from the positive x-axis will be the tangent inverse of y over x, and again Z will remain the same. Let's do an example. Let's take the cylindrical coordinates 4, 5 pi over 6, and 3 and convert those to rectangular coordinates. In cylindrical coordinates, you have R, theta, and Z given. X is equal to R times cosine theta, so that's 4 times cosine of 5 pi over 6. From your unit circle, cosine of 5 pi over 6 is negative square root of 3 over 2. The 2 on bottom cuts into 4 twice, so we have negative 2 square root 3. The y coordinate is 4 times sine of the angle given, and so that is 4 times sine of 5 pi over 6. Sine of 5 pi over 6 is 1/2. 4 times 1/2 is 2. And again, Z just stays the same. So this point, the one that you would most commonly know, negative, the XYZ ordered triple, your first number is X, so you would go into the negatives, negative 2 times square root of 3. Then in the positive Y direction, you would go 2 units. So from here, you would go 2 units. And then finally, the Z direction, positive 3. So that would take you up 3. So you would go negative X, positive Y, and then up in the Z direction. Let's go the other way, converting rectangular coordinates of, well, hang on just one second. I want to go back to that top example. R of 4 means that on the XY plane, you're 4 units away from the origin. 5 pi over 6, from the positive x-axis, you rotate 150 degrees if you were to convert that to degrees. But anyway, in radians, 5 pi over 6, that would rotate to over here, length of 4, and then up 3 from the plane. Now let's look at the second example. We're going to convert rectangular coordinates, 1 square root of 3 and 2, to cylindrical coordinates. Okay, so from the conversions on the first slide, r squared equals x squared plus y squared. X is 1, y is square root of 3, so it's 1 squared plus square root of 3 squared, that's 4. And when you take the square root of both sides, that's positive or negative 2. Tangent of theta is equal to the y over the x, square root of 3 over 1, which is square root of 3. The angle that has a tangent value of square root of 3, the first one you get to on the unit circle is 60 degrees, or pi over 3 radians. Tangent is periodic with a period of pi or 180 degrees. That's how much of an angle you open before you start repeating your values. Okay, now z stays the same, so z is 2. And I ordered those 1, 2, and 3. We found r, theta, and z. I'm just going to decide to pick the positive 2 and the first angle that tangent is square root of 3, which is pi over 4. Okay, so how that works is we're going to come from the origin, we're going to go 2 units out and plant that at a rotation of pi over 3 or 60 degrees from the positive x-axis. So we rotate out, go the proper length, and then z tells us how far up. If that happens to be a negative 2, you would go under the xy plane, but since it's positive, we go above the xy plane, and that would be our point. Let me mark that real quick. This would be our point. There we go. Back to this positive negative notation. If we decided to go with a negative 2, then we would need to go to the next angle where tangent is square root of 3, and that would be at 240 degrees or 4 pi over 3. Now if we do that, if you rotate 4 pi over 3, we're going to go 90, 180, 60 more, which would put us back in here. But then when you apply that negative to the 2, you reverse your direction. Remember, negative vectors go in opposite directions. So we would rotate 4 pi over 3 and then go 2 units in the negative direction, which would still put us here, and then up 2 units. So either one, if you want to use positive r, keep your angle in quad 1. If you choose the negative, put your angle in quad 3, and that's where that n pi generator comes in. Find an equation in cylindrical coordinates for the surface represented by each rectangular equation. We're given a rectangular equation, x, y, and z are involved in this one. Remember from our conversions, x squared plus y squared can be swapped out for r squared. And then there is no tangent value. Once we make that transition, we have r and z. Another equation in cylindrical coordinates, y squared equals x. Y was r sine theta. If we square it, then it's r squared sine squared theta. You square each component or part. X is r cosine theta, and we're just making that direct swap from the first slide's conversions. Let's bring r cosine theta across the equation. It'll go from positive to negative, and then we can factor out an r. R sine squared theta minus cosine theta equals to 0 if r, and if we solve for r, we're going to need to add cosine theta over and then divide by sine squared. Well, let's split that sine squared up into a couple of sines. So we still have cosine on top, and then we're going to split the sines on bottom. This is, you can recognize from trig, that's cotangent theta, and that is cosecant theta. And so here is the equation written in cylindrical coordinates. A second example, let's go the other way with it. Find an equation in rectangular coordinates for the surface represented by the cylindrical equation, r squared cosine 2 theta plus z squared plus 1 equals 0. Cosine double angle from trig, remember there were 3 different identities. I'm just going to choose cosine squared theta minus sine squared theta because I know that x and y are r cosine theta and sine theta driven. Now, after we change cosine 2 theta to this double angle identity, then we can distribute the r squared to both of those terms. I'm going to go ahead and move the 1 over. It'll go from positive to negative. R squared cosine squared theta is x squared. R squared sine squared theta would be y squared. So x squared minus y squared plus z squared is equal to negative 1. Remember from our last section, if we can get these equal to 1, we need that to be positive. So if you divide all the way through by a negative, then this y squared becomes positive, the x squared and the z squared become negative, and then your 1 goes positive. And this is one of those hyperboloids of two sheets whose axis lies along the y-axis. Again, from that last Google Drive document and video, if you want to print those or just have them where they're handy, I don't expect you to look at this and remember that that's a hyperboloid of two sheets. That's just way too much to try to remember in a class. In a spherical coordinate system, so think of like a globe, you would have a point P in space that's represented by an ordered triple, rho, theta, and phi. If you call it phi, that's fine. I know usually in fraternities, sororities, those are called phis. But rho, theta, phi. Okay, so go back to the globe analogy. Maybe we want to know where a certain city on the globe is located. This first number would be the radius from the center of the Earth, which I think at sea level it's 4,000 miles. So your first number, if this were a globe or the Earth, it would be 4,000. The angle in the middle would be if you were to rotate around the equator direction, like around the globe, but the equator direction, and then the third entry is another angle, but that would be like if you angled down from the North Pole. So you'd have radius of the sphere, rotation from the prime meridian, if you wanted to use a longitudinal term of a globe, and then the angle downward, which would be latitude type, from the North Pole. Rho is the distance between the point P and the origin, which would be the center of a globe. Theta is the same angle used in cylindrical coordinates, so that's not going to change. And phi is the angle between the positive z-axis and the line segment OP. So you mark a place on a globe, the angle from the North Pole down to that location, that's phi. These four groups are the conversions from spherical to rectangular, vice versa, spherical to cylindrical, and vice versa. Again, I don't expect you to memorize all this. If you want to have them handy or write your own notes out and just have these handy when you're doing these problems, that's totally appropriate. Let's go to the next slide and look at a few examples. Find an equation in spherical coordinates for the surface represented by each rectangular equation. Okay, rectangular is the one we're familiar with XY. Back in the college algebra days, you always graphed on an XY plane. In Cal 3, you up it to 3 dimensions, so then you got a Z. X squared can be replaced by rho squared sine squared phi cosine squared theta. On the previous slide, this was in one of those four groups. Just be very careful from where you are and to where you're going. In this one, we start in rectangular, we're going to spherical. So from that previous slide, you'd want to find the group that does that. Y squared is rho squared sine squared phi, sine squared theta. And then finally Z was rho cosine phi. When you square it, square each part. On the left side of the equation, rho squared sine squared phi is in common with both of those groups, so factor it out. That leaves cosine squared theta and sine squared theta in the parentheses. From trig and your Pythagorean identities, what's cosine squared plus sine squared equal to? It's equal to 1. So you have rho squared sine squared phi times 1. Well, that's just rho squared sine squared phi. The right side, we're going to leave that the same. Because rho is greater than or equal to 0, let's divide both sides by rho squared cosine squared phi. The rho squareds cancel. Sine over cosine we recognize as tangent. Because they're each squared, it's tangent squared. Square root both sides. The square root of tangent squared phi is tan phi. Square root of 1 is positive negative 1. Think back to your unit circle. Tangent is positive 1 at 45 degrees, or pi over 4 radians. And then it's equal to negative 1 at 3 pi over 4, or 135 degrees. What we have here, and you'll need to look at your e-text for a little bit of reference to when you have conical shapes versus spherical shapes. Using that first angle, phi being pi over 4, remember phi is the angle from the positive z-axis downward. So that little angle here is pi over 4, and that represents the upper cone, the upper half. The other angle, 3 pi over 4, if you rotate downward from the positive z-axis 3 pi over 4 radians, then that takes you to the lower half. Another example is if we start with a sphere, x squared plus y squared plus z squared minus 4z equals 0. Back on the conversions, we have a huge replacement here. These three terms can all be replaced with a rho squared. Z from the previous slide was equal to rho cosine phi, so that gives us rho squared minus 4 times p cosine phi, still equal to 0. Alright, so what we're at this point is we collect our terms, gather our thoughts. I see something here that I needed to remove. This part here, I just forgot to white it out. Here we go. Both terms have a rho in common, so factor out rho. That leaves a rho in the first term, because that's where it used to be rho squared. Pull the rho out there. That leaves 4 cosine phi equal to 0. Rho equals 0. P minus 4 cosine phi equals 0. Solving for rho, that's 4 cosine phi. Because P being equal to 0 is covered by this one, because think of it this way, if phi was pi over 2, what's cosine of pi over 2? 0. 4 times 0 is 0. So this one is covered by this one, and therefore that's our equation in spherical coordinates. This stuff is very tedious. I'm aware of that. Do your best. Reach out to me. I'll do my best to help you out on just reach out by email or phone, office hours. I'll do my best to help you out. Again, I know it's tedious stuff, and will do my best to help you out. So reach out if you have questions.